All right, so we're up to Chapter 9 of Introduction to Networks. So we talk about the transport layer, as the title says. So basically, we have covered the network layer very thoroughly, so we're moving one layer up the stack, and so we're looking at the transport layer. So we'll look at how transport layer protocols and services support communications across data networks, and we'll look at the purpose of the transport layer for end-to-end communication, and we'll look at both TCP and UDP, the two major options in TCP/IP, how they work, and and how they use port numbers as well. And so we'll compare TCP and UDP, and so basically both have their strengths and weaknesses, and better applications and worse applications, and so we will, as we said, compare them. And so transport layer protocols. So basically, it's responsible for establishing a temporary communication session between two applications and delivering data between them. So it's a link between the application layer and the lower layers that are responsible for the actual network transmission. And so, as the diagram says, the transport layer moves data between applications on devices in the network. Basically, transport layer tracks conversations. And so it tracks each individual conversation flowing between a source and destination application. It segments it. As I said, it chops the big data chunks into, the big data lump into smaller chunks, which we call segments. And so, of course, that makes it better for sharing the networks and also for error recovery. And of course, it identifies the application that actually sent this data, and that uses port numbers to do that, but basically. So, with conversation multiplexing, which is basically means the network is shared by multiple hosts, and so it really means, so the segmented data in smaller chunks enables many different communications being multiplexed at the same time. So smaller segments means more users can use the network at the same time. Okay, so basically this is the TCP layer model, of course, and so of course we spoke about IP last time, and so now we've got two options for a transport layer. There's both TCP, or Transmission Control Protocol, or User Datagram Protocol, UDP. And so TCP is the full strength reliability solution, and so it has a fairly large header, and it does full recovery of data if some data gets lost or damaged in transit. While UDP is the quick and dirty one, basically, and so it doesn't do reliability. It's a much smaller header, but it's much faster. So with TCP, its transport is similar to sending track packages through the mail, and so as long as, if you've got a shipping order that's broken up into several packages, and so, if you had a push bike and posted it in 10 different packages, it would be a similar kind of thing with, tracked mail. And so basically, so as I said, it gives you reliability. And so basically, there's two-way communication. So in this diagram, it's showing, you want to send a file to the server, and so then you send the first 3 segments, and then it acknowledges back saying that they've received them, and then you send the next 3 segments, and then you acknowledge back saying it's all been received, and so the file has been stored on the server. Good news. Okay, and so TCP has 3 major responsibilities, so numbering and tracking data segments, acknowledging received data, and retransmitting any unacknowledged data after a certain period of time. So this does do more things than this, but these are sort of the most common things we think of. And so basically, when you chop that data into chunks, of course you need to number those chunks so that the receiving end can then reassemble them, because across the internet, segments won't necessarily arrive in the order they were sent, because they may well take different paths on the way through, and so you need this numbering so that they can actually reassemble. Now UDP, as I said, that's the quick and dirty version. And so they call it best effort, which is the term we use for IP as well, isn't it? So there's no acknowledgement and similar to a non-registered letter. So basically you send it and you hope for the best. Now, typically UDP are either very small packets, or sorry, segments, that if you lose one or two, it won't be a major problem, or they're just very small bits of data that if you do lose it and you wait a while, you just try again. And so like DNS and DHCP would be examples of that. So TCP, you would use that for things as would have implied that require reliability. So, you know, if you're querying a database, you want all the data. A web browser, you want all the web page. You want all of your email to arrive. And so, of course, TCP is the solution for that because it does reliability, acknowledges data, resends lost data, and delivers data in a sequence order. You know, as far as the application layer is concerned, it's always in sequence order because TCP puts it that way. With UDP, if one or two of the segments of a live video stream fail to arrive, it might be a bit of a blip in the screen, but it's not going to end the world. It would actually be worse to run it on TCP, and they'd actually have to pause the stream and then wait for a resend of the data, and then you're just going to be behind. And so, do you want to speed up the video to try and catch up, or do you just end up being behind the whole time? So with UDP, it's fast, low overhead, doesn't require acknowledgements, doesn't resend lost data, and just tries its best, but doesn't try overly hard. Now, with TCP, it actually creates a session or a connection between the two hosts, the sending and receiving host. And so basically it does what's called a three-way handshake. And so basically they negotiate their connection to start with those three segments that are sent. And so after that you end up with reliable delivery, ensuring that each segment that source sends arrives at the destination, ends up being, of course, numbered in the correct order. That's always useful. And it also does flow control so that a destination machine can't be swamped by too much data, or maybe if there's congestion somewhere in the route from the source to the destination, the segments start getting lost. It will actually slow down the flow so that it will lose less segments, basically. So the TCP header, and so source ports are of course used to identify the application. So depending on what direction this segment's going in, if you're asking for a service for a web page from a web server, maybe let's say, the destination port would probably be port 80 or port 443. And so that's what's called a well-known port, and that's what a server listens on. And so that would be your destination port. And because you're using a web browser and you're the one who initiates that conversation, it's probably using a port higher than 1024. It's dynamic, but because the browser starts it, it can put that as its source port, and so the server, when it receives the request, knows what port number to send it back to. And so that's how you basically keep track, and that's how you can have more than one tab or more than one web browser running at the same time, and the pages always go to the right tab or browser. And so port numbers is certainly important in the transmission process. Now the sequence numbers are basically what number chunk is this, and the acknowledgement says I've received this numbered chunk. And so there's a header length field there to tell you how long the header is. And then there's other control bits. And so there's things like SYN, acknowledgements, FIN. There's all kinds of different control packets that are used. If you have one of those, you'd set that to, it's basically a bit for each one. And so window size is actually how it does flow control. And so it basically sets the number of bytes that can be accepted at one time. And so the checksum is basically the error checking for the segment header and the data. And so that's how you check that the data has arrived at the destination without errors, is because the sending machine has done a calculation on the header, and stored it there, and then the receiving machine will do the same calculation and compare results basically. So UDP, as I said, it's good for stuff that's small or needs to be fast and so on, and so IP telephony and streaming video are certainly two of those. And so so data is reconstructed in the order that is received. So in other words, yeah, if it takes a different route, it's going to sound a bit strange, but anyway. Any segments lost are not resent. No session establishment does not inform the sender about resource availability. So it's not connection oriented, and so basically it's send it and hope. But I'm going to say with IP telephony, you don't often have those bigger problems these days with half decent networks. So UDP is stateless protocol, so it does no tracking, and also if it needs reliability, well, the application layer is going to have to do it. And so as you can see from the header, there's not a lot there. So there's a source port, destination port, length, and a checksum, and that's it. Okay, so multiple separate communications. So users expect to simultaneously receive and send email, view websites, and make VoIP phone calls. We all do it these days. We take it for granted. And so TCP and UDP manage multiple conversations by using unique identifiers called port numbers. So as I said, so if you've got a web server, it's listening on port 80 for internet, web pages. It's listening on 110. If you've got, well, that's one of the ports for email. There's several of them actually. And then internet chat can be using port 531. But of course, there's a whole pile of other things as well. And so basically, as I said earlier, there's a source port and a destination port. The source port, of course, is the ports that's being used on the machine that sent the segment, and of course the destination port is what's being used on the destination for it. And so, as I said, if this is a host requesting a web page, it will send the destination port to be port 80 because that's a well-known web server port, and of course it will be a dynamic number for the source port. And so, yeah, so basically that's how the conversations are kept track of. So source and destination socket pairs. So basically, basically a socket is the combination of an IP address and a port number. And so you may well have seen it. So 192.168.1.7:80. And so that says to me that we have a web server with this IP address and it's listening on port 80. And so that is what's called a socket. And so basically sockets enable multiple processes to be distinguished. Source port acts as a return address basically. So source port source port from the web server to the destination is 1099, and so that host is using 1099 as the web browser. Okay, so as I said, well-known ports are normally from 0 through to 123. 1024 through to 49.151 are registered ports, and then above 49.152 are we'll call private or dynamic ports. So well-known ports, you won't normally, you would, they are, as I said, well-known. So most well-known services have got a port number below 1023. Now, above 1024, they can still be used for services as well, but they're not typically as well known. But they can also be those. They can also be used for dynamic port numbers as well. And so above 49.152 will always be dynamic or private. So well-known port numbers. So we will talk about FTP next chapter because we talk about the application layer. FTP is a bit strange. It actually uses two port numbers on a server. So port 21 is used for control of FTP connection, and 20 is used for transferring data. So port 22 is SSH, port 23 is Telnet, port 25 is SMTP or Simple Mail Transfer Protocol, 53 is DNS. Now, UDP is what's used for requests, and so it's, what's the IP address of google.com, while TCP is actually used for more server-to-server communications, so if you're doing zone transfers and the like. Port 67, dynamic host configuration protocol, so that's what a server listens on, and the reply would actually go to port 68, which is of course what the client listens on as well. So port 69 is TFTP, port 80 is a web server, and so from there we have POP and IMAP are how you download emails from your server. Two options, as I said, we will talk about that next chapter. SNMP was Simple Network Management Protocol, and of course 443 is the secure HTTP. Okay, so you can actually use a netstat command to verify connections, and so if you just type in netstat, it will just tell you active connections that are going there. And so of course that implies TCP, because UDP is connectionless, and so if you just type it in, it will actually try to resolve IP addresses and port numbers. So you can see that we have 5 different web servers we're talking to at the moment, and NetBIOS is that's a Microsoft domain protocol, and so if you do -n, it will just give you the numbers, and so it would have given all of these as being the IP addresses of what they're connected to, and it would have given either, well, it would have been port 80 for these, and I think it's somewhere around 143 or something for that. But so that's the options there. Now, TCP server processes, and so we've got some examples going here. And so, well, we've got a scenario. So we have a web server and an email server. And so the web server listens on port 80, that's the well-known port for the web server. Email is port 25. And so basically this client wants to look at a web page. And so the source port is that dynamic number that it uses, and then the destination port is port 80 to the web server. This host wants to use the email server on that server, and so the destination port is the well-known port of 25, and it's again using that dynamic port number. And so basically you request the data, and then basically when the server replies, it will actually come back the other way. And so this would basically swap around. When the server is replying, of course, the source port will be port 25, and the destination port would be 51152. And so that's what this is showing here. And because, the server. And of course, that's how you can keep track. So this is, a tab on a web browser that's asking for that. And so that information will go to the correct tab on the web browser. And of course, this will go to the correct email client, basically. So TCP, as we said, is connection oriented, and so how do we establish that connection? It's called a three-way handshake. And so basically normally it's the client that will start a connection, because the server is there waiting for a request. And so basically, the first segment that's sent is a SYN packet, or synchronize, and so it actually sends a random sequence number. So this is given an example of 100, and the control basically is one of those bits in the header, says that SYN is set to 1, and so of course the client sends it to the server, I'm assuming in this case. Now, basically, the server will actually reply back with the sequence number 300. That's its own randomly started number. Not particularly random in this, but get the idea. It will also send back an acknowledgement saying, hey, I've received your SYN packet. And so because the sequence number here is 100, it actually what's called expectational acknowledgement. Says I'm expecting sequence number 101 next. So that's basically how it replies. And then the control, it's both a SYN and a synchronize and an acknowledgement. And so then again, the client sends its ACK. So it's SYN, SYN-ACK, ACK is the three-way handshake. And so it will send sequence number 101. The acknowledgement, of course, from 300 is 301, and so we have the control field of acknowledgement set. And so that is the connection established. Now you can start transferring data. They've communicated their information. So there's more than just those. And so to close a session, it's actually 4 segments. And so when so basically when the first of the hosts decides that they don't need this connection anymore, they'll send a FIN. So it's a FIN packet, so finish. And then of course the other host will then send an ACK packet. Then that same responding host will send its own FIN packet, and then that other host will acknowledge. And so there's 3 segments to negotiate a connection and 4 segments to close a connection. So the 3-way handshake establishes that the destination device is present on the network. Hey, I can talk to it. It verifies that the destination device has an active service and is accepting requests on the destination port number. So if you're requesting port 80 on a host that is not a web server, then you won't get a reply back, basically. It informs the destination device that the source client intends to establish a communication session on that port. So the 6 bits in the control fields of the TCP segment are also known as flags. The RST flag is used to reset a connection when an error or timeout occurs. And so remember there's the 6-bit field here. Each of those bits has a meaning. So there's urgent, there's acknowledgement, there's a push, there's a reset, and there's SYN and there's FIN. And so that's basically all the only types of flags that are needed. Now, sequence numbers are assigned in the header of each packet, segment, represents the first data byte of the TCP segment. So during session setup, an initial sequence number is set that represents a starting value of bytes. Now, as I said, that's actually a random number. That's as a security measure, basically. As data is transmitted during the session, the sequence number is incremented by the number of bytes that have been transmitted. So it's actually not numbering each packet individually. They're actually just counting how many bytes have been sent. And missing segments can then be identified. And so in this case, they arrived in order 1, 2, 6, 5, 4, 3. And so basically they've reordered these segments to be in the correct order at the receiving end. Of course, they're normally sent in that order, but you know, some have gone a probably slower route or a busier route. Okay, now flow control is done by window size, as we said. So in the figure, the source is transmitting 1460 bytes of data within each segment. So window size agreed on during the is a number agreed on during the 3-way handshake. So there's not just SYNs and SYN-ACKs. There are fields for these things. And so typically a PC will not wait for 10,000 bytes before sending an acknowledgement. PCA can adjust its send window as it receives segments from PCB. So basically, the window size is how much unacknowledged data can you send. And so in this case, it must be, you know, somewhere around the 3,000 mark. I haven't seen it anywhere else. So window size has been set to 10,000. Sorry. And so basically, so we've sent some segments and they've been acknowledged back. And so it's also changed the window size. And so now they can actually send more. But so basically, the acknowledgements can do more than just say, I've received the data. You can also change the window size. So if the host is extra busy, you can decrease it, or maybe there's congestion. You can decrease it as well if segments are getting lost. But also, if you've ever noticed, when you download a fairly big piece of data, you'll notice that the download speed will start relatively low, will increase until a point, and then it will actually decrease, and then it will sort of hover around a little bit. And so that's basically the receiving host and all that. When we got all that without errors, let's increase the window size a bit. Let's try and speed this up. And so it will keep increasing the window size until segments start getting lost, and then it will sort of wind back the window size until it stops being, until the missed segments stop, basically. And so then every now and then it will try to up the segment size again, because you know, that might have been temporary congestion, and so let's see if we can get the download going quicker. And so it's a very dynamic thing. Okay, so congestion avoidance. Basically, congestion causes retransmission of lost TCP for segments, so of course that makes the congestion worse. So to avoid and control congestion, TCP employs several congestion handling mechanisms like timers and algorithms, and so that is when it would reduce window sizes if you start losing segments. Okay, now of course UDP is a low overhead protocol, and so it will, yeah, so it doesn't do a lot of that stuff, and so it just tries to do things as quickly as it can. And so of course it's not connection oriented as well. So UDP reassembles data in the order that it's received and forwards it to the application. If the order is important, well, then the application layer needs to figure out what order it came in. Okay, so UDP server processes and requests, and so the remote authentication dial-in user service, or Radius service shown, provides authentication, authorization, and accounting services to manage user access. And so basically it's listening on port 1812. Client requests to servers have well-known port numbers as the destination port. And so basically this is a DNS server as well as a Radius server. And so in this instance, this client wants a DNS name resolution, while this one wants to use the authentication service. And so, of course, the destination port is for port 53 for DNS and 1812 for Radius. And so, as we said, we use random port numbers again for the clients, but because they're the ones that initiate it, the server knows what port they came from. So the response, of course, means for DNS, the source port from the server will be 53 and back to that dynamic port number, and the same again with the Radius server. The source port will be 1812 and the destination port will be there. And so, of course, then this client will have received it, and then it will pass it on to whichever whichever service wants the DNS resolution. Of course, this will go to whatever needs authentication. Okay, so some common applications that use TCP. So HTTP, web server. Yeah, we certainly want our web page, all of our web pages. So that's certainly a good reason to do that. FTP, again, not much good getting most of the file. We want all of the file. SMTP, mail. Yeah, we prefer to read all of our email and not just part of it. And Telnet, yeah, again, we want reliability for that as well. So UDP, and so DHCP, again, basically there are four segments that get sent for DHCP. Why would you do 3 setup and 4 teardown for 4 other segments? So we've got 7 on top of the 4 we need. And so that's more overhead than there is actual data going. And so that'd be crazy. If the DHCP request doesn't work the first time, try again. DNS, much the same. It's only actually 1 segment each direction for DNS. So yeah, an extra 7 segments for that would be crazy. SNMP, it just tries again. TFTP was only ever designed to do small files. It was actually was sort of used by BootP to send configuration data. And so, of course, VoIP, again, you wouldn't hold up a phone conversation because you lost a segment. So that's crazy, and the same with video as well. So that's the end of chapter 9. And so we've looked at how transport layer protocols and services support communications, and we've compared TCP and UDP on how they support end-to-end communication. Okay, there's the logo. So that's chapter 9. So chapter 10 is the application layer, and then chapter 11 is actually sort of an overall scenario, but also introduces some security issues as well. So I'll see you again later.